Hello everyone, in the lecture today we will continue the introduction about the Asphalt technology in super pale mix design. In the previous lecture we introduced the material selection for super pale mix design. In this lecture we will focus on the second step, the design about the aggregate structure. Basically the super pale mix design defines 5 steps for the selection of aggregate structures. At first we will establish several trial blends with different aggregate structures, and then we will check the aggregate properties, especially the grain size distribution. After that, we will apply the gyratory compactor to compact the specimen, and then we will conduct the volumetric calculation to estimate the properties of the trial blends. Finally, based on the results from the volumetric calculation, we will select the appropriate aggregate structures for the super pale mix design. In the step of design aggregate structure, the most important content we have to consider is aggregates, which is usually referred as the soils that has been processed or sorted in some way. For the analysis of the soil, the most important part we want to understand is the aggregate size. There are two variables applied for the definition of aggregate size. The first one is the nominal maximum aggregate size. To identify the nominal maximum aggregate size, we have to apply the sieve analysis. And in this analysis, we will find out the first sieve to retain more than 10% of the particles. After that, one size larger than the first sieve is defined as the nominal maximum aggregate size. The second variable applied for the aggregate size is called the maximum aggregate size. It is simply defined as one size larger than the nominal maximum size. In the second step, the most important thing we want to estimate is the aggregate gradation, which is the grain size distribution of the particles in the selected aggregate. In order to find out the aggregate gradation, we have to recall the 0.45 power chart, which is shown in the figure here. In this figure, the horizontal axis is scaled down with 0.45 power. So the value here with the sieve size of 19.0 is actually applied the true value as 19.0 to the power of 0.45, and this will be applied for the other sieve size. With this power chart, we are able to define the maximum density line. It will start from the origin at 0 and join the linear line from 0 to the maximum size, where the percentage there is 100. In addition, at the maximum density line, there is one region called restricted zone, where we don't want to apply any percentage passing for the specific sieve size within this restricted zone. Moreover, in this power chart, we have some upper and lower bounds about the percentage passing for the specific sieve size. For example, if we consider the nominal maximum size, we have the upper bound and lower bound about the percentage. For 9.5 sieve size, we have upper bound, and similarly we will have the constraints for the different sieve size. With that, we can design some trial blends based on the constraints, and this will be applied for us to select an appropriate aggregate gradation. So we can choose something will satisfy all the constraints and avoid the restricted zone. The figure here shows one sample about the aggregate gradation, where you can see that it will satisfy all the constraints that we specified in the previous page. In addition, for the super pale mix design, we want to identify 3 trial blends, which means we need to specify 3 lines. This is one example, and we can identify some other ones, but all of them should satisfy the constraint in this 0.45 power chart. The table here identifies the gradations of 3 trail planes for the super pale mix design, which will show the percentage passing for different seal size. All these 3 gradations will satisfy the constraints in the previous 0.45 power chart. The figure here illustrates the aggregate gradations defined in the previous table. Basically, you can see that the trail blend 2 will have more cross contents than trail blend 1 and trail blend 3. This table summarizes the sample aggregate structures in the 3 trail blends. Basically, for trail blend 1, the percentage of number 1 stone is 25, and for trail blend 2, is 30%, and for trail blend 3 is 10%. You can also find out the percentage of the other types of the particles applied for the aggregates. With the selected aggregate structures for the trail blends, we also need to check the aggregate property which we defined in the previous lecture. We have the coarse angularity, fine angularity, flat or elongated particles, and sand equivalent. For the example, we have the minimum and maximum requirements about different properties. For example, for coarse angularity, we want the percentage of 1 plus fracture phase as 95% minimum, and for 2 plus fractured phase as 90%. For all the 3 blends, we have all these conditions are satisfied. Also, we need to check the other 3 properties: fine angularity with the minimum percentage as 45%. All these 3 blends will have the percentage higher than 45. And for flat or elongated particles, they all have the value around 0%, which will be less than 10% from the criterion. And for the sand equivalent, the minimum value is 45. In these 3 trail blends, they are all higher than 45. In addition, we also want to find out the value of GSB and GSA for the future estimation about the aggregate properties. Once the aggregate property of the 3 trail blends has been checked and we found that they all satisfy the criterion, then we can go to the third step for compacting specimen. The page here lists the 5 steps for the specimen compaction. First, we have to establish the trail asphalt binder content. For each trail blend, we need to specify 1 trail binder content. And then we have to establish the aggregate weight. After that, we will conduct the process of batching, mixing, and compacting specimen. And during the compaction, we need to determine the initial and designed number of the gyrtation for the gyratory compactor. And after that, we will determine the mixture property at n initial and n design. Before we conduct the specimen compaction, we have to choose the appropriate amount of aggregates for the specimen in the experiment. In the specimen preparation, there are 2 requirements for different tests. The first one is about the specimen height for the gyratory compaction. Usually the specimen is prepared in the cylinder. The diameter is set around 150 millimeters. If we are conduct the mixed design, then the height should be selected around 115 millimeters with a weight of 4.7 kilogram. If we are conducting a moisture sensitivity analysis, then the height is 95 millimeters with the weight of 3.5 kilogram. In the second step, we also want to understand the GMM for the specimen, which would be the maximum specific gravity. You can see more details about definition in the third tutorial. Usually the estimation about GMM is conducted with a loose specimen, and the sample size for the estimation of GMM varies with the NMAS, which would be the nominal maximum aggregate size. That is defined in the previous pages. If the nominal maximum size is around 19 millimeter, then the weight of the sample should be selected as 2 kg. If it's 12.5 millimeter, then we will only need to choose 1.5 kg of the sample. The figure here shows the samples of the trail blends used in the experiment. In each trail, there will be aggregates which will follow the designed aggregate structure. Also, we have several samples for each trail, and each sample will have different values of the asphalt binder. And this information will be used for the third step in the super pale mix design, that is the design of the asphalt binder. With the selected aggregates in each trail, we will then add some asphalt binder to the aggregates, and then mix them together. After the mixture with the asphalt binder, the samples will be stored in the oven at the compaction temperature for 2 hours, and this step is applied to reproduce the short-term aging effect. After 2 hours, the samples will be moved out from the oven and stored in the mold for the compaction. The specimen compaction is conducted by an gyratory compactor. The figures here shows the examples about the machine applied for the super pale gyratory compaction. This is actually the third experiment we will do in this class. The super pale gyratory compaction (SGC) is applied to simulate the field densification of the asphalt mixture. It's able to analyze the impact of the repeated traffic load and climate change to the road pavement. In addition, it's able to accommodate large aggregates, measure compatibility of the aggregates, and conduct to quality control of the asphalt mixture. The SGC test applies Texas equipment with French operational characteristics. In the test, the machine will use a mold with a diameter of 150 millimeters and is able to compact aggregates with the nominal maximum size up to 37.5 millimeters. Also, it has a height recordation to identify the height of the specimen during the experiment. In the experiment, the pressure applied to the specimen is set as 600 kilopascal and is a constant value for the whole experiment. In addition, the rotation angle is set as 1.25 degree. Also, the rate of the rotation is set as 30 gyratation per minute, and we will try to identify the height during different number of the rotations in the experiment. The figures here shows the components of the gyratory compactor. It has the mold for the generation of the specimen and loading ram to apply the pressure to the specimen. Also, we will have the control and data acquisition panel to read the information during the experiment. And the mold is actually set on the rotating base, where we are able to enable the machine to rotate the specimen during the experiment. The figure here shows the compaction curve during the test. The horizontal axis is the log number of the gyrations, and the vertical axis shows the percentage of the maximum specific gravity. Basically, we can see that there exists a linear relationship. By increasing the number of the gyrations, the maximum specific gravity will be higher, which means that the density of the specimen will be larger. In the SGC test, the density of the specimen is usually evaluated at 2 points, N initial and N design. Here, N initial is the initial number of the gyration, which is applied to reproduce the compactability during the construction of the pavement. And N design is the design number of the gyration, which is applied to reproduce the desired traffic load. The table here summarizes the values of N initial and N design under different traffic levels. The traffic level is measured as ES/ALs in millions. So when the traffic level is less than 0.3, the N initial value is set as 6 and design is set as 50. And basically, with a higher number of the traffic level, the number of gyration at initial and design will all be larger. and the increments about the N design will be more significant than N initial. In the last step of the design aggregate structure, we want to check the properties of the mixture. Actually, there are some requirements about the super-pale mixture, including the requirements in specimen height, mixture volumetrics, dust proportion, and maximum specific gravity at N initial. Also, for the mixture volumetrics, we want to calculate the air voids, the voids in the mineral aggregates, VMA, and voids filled with asphalt, VFA. In the step of the design aggregate structure, we have 3 trail planes, and with the SGC test, we can find out the properties of each trail. In the test, we will record the trail binder contents. For example, in this case, we will set a 4.4% for all the 3 trails. And then we will measure the maximum specific gravity at N design and N initial. Also, we will do the volumetric calculation to find out the air voids, VMA, and VFA. We will also measure the dust proportion. In the experiment, we found that the air voids is around 4%, but it's not exactly 4%. However, in the estimation about the volumetrics, we want to make sure that all the contents and the properties are estimated at 4% air voids. In that sense, we have to convert the properties to 4% air void scenario. Basically, we need to convert 2 contents. The first one is the asphalt content, and the second one is the VMA. For asphalt content, we will call the equation here, PBE equal to PBI minus 0.4 times 4 minus VA. Here, PBE is the estimated design asphalt content at 4% air void, and PBI is the asphalt content in the trial blend. Here, VA is a air void. For VMA, we will call the second equation. VMA estimated value will equal to VMAI plus C times 4 minus VA. VMAE is the estimated VMA at the designed asphalt content, and the VMAI is the initial VMA of the trial blend. And C here is the constant. It will be 0.1 when the air void is less than 4%, and it will be 0.2 if the air void is higher than 4%. Now we can see how we can convert the asphalt binder and VMA at the air void of 4%. First, let's check the trial 1. The air void is 3.8%, and we will need to call the equation PBE equal to PBI minus 0.4 times 4 minus VA. For trial 1, PBI is 4.4 minus 0.4 times 4 minus the air void is 3.8, which will give the result as 4.3. So we have the revised value as 4.3%. And similarly, we can apply the equation VMA equal to VMAI plus C times 4 minus VA. For trial 1, VMAI is 12.7. So that is 12.7 plus, we know that air void here is less than 0.1. So we have capital C as 0.1 times 4 minus 3.8. So the value is 12.7, which is almost the same to the previous one. So we'll keep this the same. And you can apply the similar calculation for the trial 2 and 3. With that, we will have the asphalt content for trial 2 as 4.5%, and trial 3, 4.7%. For the VMA, we have the value as 13% for trial 2, which is the same, and for trial 3, it becomes 13.3%. And we will have the modified air voice are all as 4%. And we will use the updated value to check which one is appropriate for the aggregate structure. This figure summarizes the volumetric design criteria for asphalt mixture from the SGC test. In this table, we can also see the criteria applied to different traffic levels. The first column shows the traffic level in ESAL in millions, and the second two columns shows the maximum specific gravity at initial and design number of gyration. We also have the criteria about VMA, VFA, and dust proportion. For example, if the traffic level is less than 0.3, then the maximum specific gravity at the N initial will be less than 91.5. For N design, it should be always close to 96. We have more details about the criterion in VMA in the future. For VFA, the value should be around 70 to 80, and for the dust proportion, it should always be between 0.6 and 1.2. Now let's check one example to see how we can use these criteria to identify appropriate aggregate structures from the trial planes. In this example, we assume that the traffic load is set as ESAL is higher than 3 million. And with this condition, we will have the criterion for the maximum specific gravity at N initial as less than 89%. For air voice is set as 4%. VMA should be higher than 13%. And VFA is between 65 and 75%. Also for the dust proportion, it's always between 0.6 and 1.2. And then with this criterion, we can check each trial to see whether they satisfy the conditions. For trial 1, the asphalt content is 4.3%. And we have the maximum specific gravity at the initial as 86.9%, which is smaller than 89%. This condition is satisfied. Air voice is 4%. VMA is 12.7%, which is less than 13%. So this condition is not satisfied. For VFA, it's 68.5%. It's between 65 and 75, and it's satisfied. Dust proportion is 0.9, which is between 0.6 and 1.2. So in general, we can claim that the trial 1 is not appropriate for the design, while for the other two trials, 2 and 3, they all satisfy all the requirements, and we can claim that they are appropriate aggregate structures for the pavement design. If we find now the 3 trial planes in the experiment satisfy the requirements, then we have to consider an alternative method. We can either recombine the aggregates to form further trial planes so that they can satisfy the criteria, or we can obtain new materials such as new aggregates, asphalt binders, or modifiers. With those, we are trying to make sure that the aggregate structure will satisfy those requirements. So that's all about the lecture today. Thank you very much for your attention. In this lecture, we just focus on the step about the design of the aggregate structure. In the next lecture, we'll try to finish all the rest contents in the super pale mix design.